From where we stand, we see our home, a pale blue dot floating in the infinite void. But the universe began billions of years ago in a burst of fire and light. From this small blue point, we begin a journey through the vast fabric of the cosmos, a journey that will take us to the edges of space and time, and perhaps to the edges of human understanding itself. It all started with the Big Bang, a moment of creation that set the universe on a path of endless expansion. But what few people know is that the universe might be breathing. 13.8 billion years ago, there was nothing. No space, no time, no matter. And then, in an instant smaller than a fraction of a second, everything erupted into existence. The Big Bang wasn't an explosion in space. It was an explosion of space itself. Every point in the universe was the center of this cosmic eruption. Space expanded faster than the speed of light, carrying with it the seeds of everything that would ever exist. In the first trillionth of a second, the universe was unimaginably hot, quadrillions of degrees, so hot that the fundamental forces of nature were unified into one. Gravity, electromagnetism, the strong and weak nuclear forces, they were all one thing. But as the universe expanded, it cooled. And as it cooled, these forces began to separate like streams branching from a river. First gravity split off, then the strong nuclear force, then the electromagnetic and weak forces separated from each other. This wasn't just expansion. This was creation itself, happening in real time. Within the first 3 minutes, the universe had cooled enough for the first atomic nuclei to form. Protons and neutrons fused together, creating hydrogen and helium, the simplest elements. These would become the building blocks of stars, planets, and eventually us. For thousands of years, humanity believed the universe was static, eternal and unchanging. The stars were fixed in their celestial sphere, and everything remained as it had always been. But in 1929, an astronomer named Edwin Hubble made a discovery that would shatter this ancient belief forever. Hubble was studying distant galaxies, measuring their light. And he noticed something strange. The light from these galaxies was shifted toward the red end of the spectrum. This is called redshift, and it's the same effect you hear when an ambulance passes you. The sound waves stretch out as it moves away. Hubble realized that these galaxies weren't just moving away from us. They were all moving away from us. And not just from us. They were moving away from each other. The farther away a galaxy was, the faster it was receding. The implications were staggering. If everything is moving apart now, then in the past everything must have been closer together. Wind the clock back far enough, and you arrive at a single point, the moment of the Big Bang. The universe wasn't static, it was expanding. It had been expanding for billions of years, and it was still expanding right now, at this very moment. But Hubble's discovery raised an even deeper question. How exactly was the universe expanding? Was it steady and constant, like a balloon inflating at a fixed rate? Or was something more complex happening? For decades after Hubble's discovery, astronomers assumed the expansion of the universe was slowing down. After all, gravity should be pulling everything back together, right? The universe should be expanding, yes, but gradually decelerating over time. But at the end of the 20th century, two independent teams of astronomers made a discovery that shocked the world. They were studying Type Ia supernovae, massive stellar explosions that shine with a predictable brightness. These supernovae are so powerful they can be seen across billions of light years, making them perfect cosmic distance markers. What these teams discovered was impossible. The distant supernovae were dimmer than they should be. And there was only one explanation. The universe wasn't slowing down at all, it was speeding up. Something was pushing the universe apart, causing the expansion to accelerate. This mysterious force was given a name, dark energy, and it makes up about 70% of everything in the universe. But here's where it gets truly fascinating. The expansion isn't accelerating smoothly and uniformly. Recent observations suggest the rate of expansion changes over cosmic timescales. Sometimes it accelerates faster, sometimes the acceleration slows. Astronomers have discovered that the universe doesn't expand in a constant way. In certain eras, the expansion accelerates. In others, it slows down. as if the cosmos itself were inhaling and exhaling slowly in a cycle that lasts billions of years. This cosmic breathing isn't random, it follows patterns, rhythms that span epochs we can barely comprehend. One breath of the universe might take 5 billion years. Another might take 10 billion. We're living inside one of these breaths right now. We're in an era of accelerating expansion, an exhale, if you will, but there have been periods in cosmic history when expansion slowed, when the universe inhaled. So what causes this breathing? What makes the universe speed up and slow down? The answer lies in the ongoing battle between two fundamental forces, gravity and dark energy. Gravity wants to pull everything together. It's the force that makes planets orbit stars, that makes galaxies cluster together, that once threatened to collapse the universe back into a point. Gravity is the universe's tendency to gather itself, to compress, to inhale. Dark energy is the opposite. It's a property of space itself, and the more space there is, the more dark energy exists. It pushes everything apart, driving galaxies away from each other at ever-increasing speeds. Dark energy is the universe's exhale, its expansion into the void. Throughout cosmic history, these two forces have been locked in a cosmic tug-of-war. In the early universe, gravity was stronger. Matter was densely packed, and gravitational attraction was intense. The expansion slowed. The universe was catching its breath after the violent explosion of the Big Bang. But as the universe expanded, matter spread out. Galaxies moved farther apart. And as the average density of matter decreased, gravity's influence weakened. Meanwhile, dark energy grew stronger because there was more space for it to fill. About 6 billion years ago, dark energy overtook gravity. The expansion began to accelerate. The universe started its long, deep exhale, an exhale that continues to this day. But this balance isn't fixed forever. The ratio between matter, dark energy, and the curvature of space itself can shift. Some theoretical models suggest the properties of dark energy might change over time, that it might not be a constant after all. If dark energy weakens in the future, gravity could regain dominance. The expansion might slow again. The universe would inhale once more, and if dark energy strengthens, the exhale could become so powerful that it tears the fabric of space itself apart. Galaxies would be ripped away from each other. Solar systems would dissolve. Eventually, even atoms could be torn apart in an event called the Big Rip. The universe's breath might be slow and gentle, spanning billions of years, or it might become violent and catastrophic. We don't yet know. How do we know any of this? How can we measure something as vast and slow as the breathing of the universe? Astronomers use several cosmic tools, each like a different instrument in an orchestra, all playing together to reveal the symphony of expansion. First, there are those type Ia supernovae we mentioned earlier. These stellar explosions shine with a known brightness, allowing us to calculate their distance with remarkable precision. By comparing their actual distance to their redshift, we can measure how fast the universe was expanding at different points in cosmic history. Then there's the cosmic microwave background, the oldest light in the universe. This faint radiation fills all of space, a remnant from when the universe was only 380,000 years old. By studying tiny temperature fluctuations in this ancient light, we can read the universe's history like a cosmic fossil record. Astronomers also study baryon acoustic oscillations, sound waves from the early universe frozen into the large-scale structure of galaxies. These act as a standard ruler, stretching across billions of light years, allowing us to measure how much the universe has expanded over time. And there are gravitational waves, ripples in space-time itself, caused by colliding black holes and neutron stars. These waves carry information about cosmic distances and expansion rates across the universe. But here's the problem. When we use different methods to measure the expansion rate, we get different answers. This is called the Hubble tension, and it's one of the biggest mysteries in cosmology today. Some measurements suggest the universe is expanding at about 67 kilometers per second per megaparsec. Others suggest 73. That might not sound like a huge difference, but it's enough to indicate that something fundamental in our understanding is wrong. Could this discrepancy be evidence of cosmic breathing? Could the expansion rate be changing in ways we haven't fully accounted for? Some scientists think so. Here's where this story becomes deeply personal. Because if the universe breathes, what does that mean for us? We are not separate from the universe. We are the universe experiencing itself. Every atom in your body was forged in the heart of a dying star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in stellar furnaces billions of years ago. When those stars exploded, they scattered their elements across space. Those elements drifted through the cosmos, gathering in clouds of gas and dust. Eventually, they collapsed under their own gravity, forming new stars and planets. Our solar system, our Earth, and ultimately, you. You are made of stardust, not metaphorically, literally. The atoms that compose your body are ancient travelers, billions of years old, survivors of cosmic violence and creation. And if the universe has its own rhythm, its own breath, then perhaps we, made of the same stardust, are also dancing to the heartbeat of infinity. Consider the rhythms within your own body. Your heart beats about 60 to 100 times per minute. Your lungs expand and contract 15 to 20 times per minute. Your brain generates electrical waves that oscillate at different frequencies, depending on whether you're awake, asleep, or dreaming. These aren't isolated phenomena. These rhythms connect to larger cycles, the 24-hour circadian rhythm that governs your sleep and wakefulness, the lunar cycle that affects tides and biological processes, the annual cycle of seasons that has shaped life on Earth for billions of years, and beyond that, the orbit of Earth around the Sun. The orbit of our solar system around the galactic center, a journey that takes about 225 million years, the movement of our galaxy through space, drawn by the gravitational pull of the Virgo supercluster. We are nested rhythms within rhythms, cycles within cycles. From the beating of your heart to the breathing of the universe itself, everything pulses with its own frequency. Some scientists speculate that this isn't coincidence. The universe might have a kind of fundamental resonance, a cosmic frequency that echoes through all of existence at every scale. From quantum fluctuations to the largest structures in space, everything might be vibrating to the same underlying rhythm. So what happens next? Where is this cosmic breath taking us? If current observations are correct, we're living in an age of increasing expansion. Dark energy is winning its battle against gravity. The universe's exhale is growing stronger. In about 4 billion years, our Milky Way galaxy will collide with the Andromeda galaxy. This might sound catastrophic, but galactic collisions are actually slow and graceful cosmic dances. The stars are so far apart that very few will actually collide. Instead, the two galaxies will merge, forming a new elliptical galaxy that astronomers have already nicknamed Milkomeda. But this merger will be one of the last great cosmic gatherings. As dark energy continues to push the universe apart, galaxies beyond our local group will recede from us faster and faster. Eventually, they'll cross the cosmic horizon, the boundary beyond which light can no longer reach us, no matter how long we wait. In 1 trillion years, an observer in our galaxy would look out at the night sky and see nothing. Just darkness and the stars of their own galaxy. All evidence of the larger universe would have vanished beyond the expanding horizon. If a civilization arose at that time, they would have no way to discover that the universe was expanding, no way to learn about the Big Bang, no way to know there were ever other galaxies at all. We are living in a privileged moment in cosmic history, a brief window when the universe is old enough to have created complex structures like galaxies, stars, and life, but still young enough that we can observe and study the wider cosmos. But the exhale continues. In 10 to the 100th power years, a Google years, even the longest-lived stars will burn out. The universe will enter the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, and black holes. Eventually, even black holes will evaporate through a quantum process called Hawking radiation. In 10 to the 106th power years, the last black holes will dissolve into radiation, leaving nothing but a thin sea of particles spreading through an ever-expanding void. The universe will have breathed its last exhale, and there will be no inhale to follow. Just eternal expansion, eternal cooling, eternal darkness. This is the heat death of the universe, the final equilibrium state where entropy reaches its maximum, where no energy remains to do work, where nothing changes anymore because there's nothing left to change. But that's not the only possible future. The universe's breath might take a different path. If dark energy weakens over time, gravity could eventually regain control. The expansion would slow, then stop, then reverse. Galaxies would begin falling back toward each other. Space itself would contract. This scenario is called the Big Crunch. The universe would compress, becoming denser and hotter, like watching the Big Bang in reverse. Eventually, everything would collapse back into a singularity, a point of infinite density and temperature. Some physicists speculate that the Big Crunch might not be an ending, but a transition. Perhaps the universe bounces back, exploding into a new Big Bang. This is the oscillating universe model, an eternal cycle of expansion and contraction, breathing in and out forever. In this model, our universe might be just one breath in an infinite series. There might have been universes before ours, each expanding from its own Big Bang, then contracting into a big crunch, then rebounding into a new cycle. Each cycle might last hundreds of billions of years. The universe breathes very, very slowly, but it never stops breathing. Another possibility is the Big Rip. If dark energy not only persists but grows stronger over time, the expansion could become so rapid that it tears apart the fabric of space itself. First, galaxy clusters would be ripped apart, unable to hold themselves together against the accelerating expansion. Then individual galaxies, then solar systems, then planets. Eventually, even atoms would be torn apart. The electromagnetic force holding electrons to nuclei would be overcome by the expanding space between them. Even atomic nuclei would split, protons and neutrons separating. Finally, the quarks inside those particles would be torn from each other. Space itself would fragment into disconnected pieces. The universe wouldn't just die, it would be destroyed at the most fundamental level. This would happen in about 22 billion years, if current estimates of dark energy's strength are correct. But if dark energy is growing stronger faster than we think, it could happen much sooner. The truth is, we don't know which future awaits us. And that uncertainty reveals something profound. Despite all our progress, despite all our observations and mathematics and theories, we still don't understand what most of the universe is made of. We call it dark matter and dark energy. But these names are just placeholders for our ignorance. We know dark matter exists because we can see its gravitational effects on galaxies and galaxy clusters, but we don't know what it is. It doesn't emit light, doesn't absorb light, doesn't interact with ordinary matter except through gravity. Dark energy is even more mysterious. We don't know if it's a property of space itself, a new fundamental field, or something else entirely. We don't know if it's constant or changing. We don't know why it has the strength it does. Theoretical calculations suggest it should be 10 to the 120th power times stronger than observed, one of the largest discrepancies in all of physics. Together, dark matter and dark energy make up about 95% of the universe. Everything we can see, every star, every planet, every galaxy, every atom, is just 5% of reality. We're living in a cosmos we barely comprehend. And yet, from this small island of understanding, we're trying to map the entire ocean. We're trying to understand not just what the universe is, but how it changes, how it evolves, how it breathes. Some scientists propose that the answer lies in quantum mechanics. At the smallest scales, reality is fuzzy and probabilistic. Particles pop in and out of existence. Space and time themselves might be granular, made of discrete units smaller than anything we can measure. Perhaps dark energy emerges from quantum fluctuations in the vacuum of space. Perhaps the breathing of the universe is driven by quantum processes we can't yet detect. Others look to modifications of Einstein's theory of gravity. General relativity has passed every test we've thrown at it for over a century, but perhaps it's incomplete. Perhaps at cosmic scales, gravity behaves differently than we think. Perhaps the breathing isn't caused by dark energy at all, but by a subtle modification to the laws of gravity themselves. Meanwhile, we live our lives inside this cosmic breath, mostly unaware of it. The expansion of space is happening everywhere all the time, but we don't feel it. We don't see it. Our daily experience is completely unchanged by the fact that the universe is exhaling around us. Why not? Because gravity holds us together at small scales. The atoms in your body aren't expanding. The Earth isn't expanding. Even our galaxy isn't expanding. The gravitational bonds within these structures are far stronger than the expansion of space trying to pull them apart. Space only expands in the voids between galaxy clusters, where gravity is weak and dark energy can dominate. If you could somehow place a ruler across billions of light years, you'd eventually see the ends moving apart. But place that ruler on Earth, and it stays the same length forever. This creates a strange duality. On cosmic scales, the universe is dynamic, evolving, breathing. But on human scales, everything seems stable and permanent. We evolved in this stable bubble, protected from cosmic change by the strength of gravity. And yet we're not completely disconnected. The universe's breath determines the ultimate fate of everything we know and everything we could ever become. It sets the timeline for cosmic evolution. It determines how long stars will shine, how long galaxies will exist, how long the night sky will be filled with light. It even affects how we understand our own existence. The fact that we're here now in this era of cosmic history tells us something profound. We couldn't exist in the very early universe. It was too hot and chaotic. We probably can't exist in the far future universe. It will be too cold and empty. We exist in the middle chapters of the cosmic story, during a relatively brief window when the universe has cooled enough for complexity to arise, but hasn't yet expanded so much that all the energy has dissipated. This is sometimes called the habitable epoch of the universe. Just as planets have habitable zones where liquid water can exist, the universe itself might have a habitable epoch when life is possible. We're living in it right now. So what does it mean that the universe breathes? Is it just a metaphor, or is there something deeper here? In one sense, it's purely metaphorical. The universe isn't alive. It doesn't have lungs or consciousness. The accelerating and decelerating expansion isn't driven by intention or purpose. It's just physics, the interplay of matter, energy, and the structure of space-time. But in another sense, the metaphor reveals something true. The universe does have rhythms. It does have cycles. It does change over time in ways that resemble breathing. Periods of faster expansion followed by periods of slower expansion, driven by the ongoing balance between opposing forces. And if we expand the metaphor even further, we might ask, what is breath but the exchange of energy and matter with the environment? When you breathe in, you take in oxygen and expel carbon dioxide. You're participating in a cycle that connects you to plants, to the atmosphere, to the chemistry of Earth itself. The universe, too, is constantly exchanging and transforming energy and matter. Stars breathe, in a sense, fusing hydrogen into helium, converting mass into energy, eventually releasing that energy back into space. Black holes breathe, slowly evaporating through Hawking radiation. Even space-time itself breathes, expanding and contracting in response to the mass and energy it contains. Everything is connected through these cycles. The breath you're taking right now contains atoms that were once part of dinosaurs, of ancient seas, of distant supernovae. You're inhaling the universe and exhaling yourself back into it. This isn't mysticism, it's physics and chemistry. But it's physics and chemistry that reveals a profound interconnectedness, a web of relationships that spans from the quantum to the cosmic. We are not separate observers studying the universe from outside. We are the universe studying itself. We are the cosmos become conscious, looking back at its own origins, contemplating its own destiny. From where we stand, we see our home. A pale blue dot in an expanding cosmos, riding a wave of dark energy toward an uncertain future. We are living inside the breath of the universe. We are part of its rhythm, its cycle, its story. The universe began in fire and light, and it may end in darkness and cold. Or it may crunch back down to a point and rebound into a new beginning. Or it may tear itself apart at the seams. We don't know. But we do know this. We are here now, in this moment, able to ask these questions and marvel at the answers we find. We know we're made of atoms forged in stellar furnaces. We know we're riding an acceleration that began 6 billion years ago. We know we're part of a cosmos that stretches back 13.8 billion years and forward into an unimaginably distant future. And we know that the universe has rhythms, slow, deep cosmic rhythms that span billions of years, rhythms we're only beginning to detect and understand. If the universe is breathing, then perhaps we, made of the same stardust, subject to the same laws, part of the same story, are also dancing to the heartbeat of infinity. Every breath you take connects you to this cosmic rhythm. Every heartbeat echoes the pulse of creation itself. You are ancient and young, small and vast, temporary and eternal. You are the universe breathing.